Okay, for copper 2 sulfate solution, okay, copper sulfate undergoes visible changes with certain regions. Okay, therefore, okay, for this one, okay, I wrote a lot of notes over here so that we can learn. Yep. So here you see these are the part that where sometimes I told you, okay, they certain things you need to memorize. Okay, so sometimes, okay, for those who have revised this chapter by heart, then it's going to be very useful. Okay, because why? Okay, in this particular year, okay, they ask 4 marks. Okay, but for me, if you ask, yeah, 4 marks is considered to be too little. Okay, too little for the effort, okay, that you will take to memorize all this. Okay, so therefore, okay, I will just suggest, okay, just learn things by heart now. Okay, but be ready. Okay, be ready to accept the fact that, okay, maybe you won't if you don't have time, okay, to memorize all this. Okay, be ready to let go certain number of marks. Okay, so but here, okay, as a teacher, okay, what I can tell, okay, I can tell that, okay, please remember this. Please remember this. So it depends on how you want to take it. Okay, like for me, okay, let's learn. Okay, let's learn if they ask questions on this. What are the things that you need to remember? What are the things that we need to really focus? Okay, like whenever I have this copper sulfate, okay, copper sulfate means copper sulfate is in a form of CuH2O6, okay, and then 2 plus. So now when I add a few drops of ammonia, what you need to remember, okay? The thing that you need to remember when you just add few drops of ammonia and the difference between the when you're adding excess of ammonia is going to be, we are going to assume a few drops of ammonia. We are going to assume there is no ammonia. Okay, just assume you are not adding any ammonia. Okay, you are going to have, okay, because it's ammonia solution, okay, you are going to have the water itself will give you the OH minus. The ligand that we are interested when you add few drops of ammonia will be the OH. So I want you to think as though they are adding OH minus. Okay, as though they are adding OH minus. So what do you see, okay, when you add OH minus over there? Okay, you will see a pale blue precipitate. Do remember this, okay, pale blue precipitate. So it means this reaction is the same as you are adding excess sodium hydroxide. Okay, I want you to remember this. Okay, this reaction is the same as you are adding excess sodium hydroxide. So you will get the pale blue precipitate. And the equation is also going to be the same. Okay, what is going to be the equation? The equation is going to be something reacting with OH. So this is the equation, okay, plus OH minus, okay, there is going to be a ligand exchange over here where you are going to remove 2 moles of water and you are going to get this, okay. Do remember there is no charge, okay, because OH minus is -1, Cu2 plus, so you have 2 negative ones and then it will cancel and it will give you the solid. That's why it's a precipitate. Okay, it's a ligand displacement reaction. So if they ask you identify the formula of the complex ion that is formed or the one that is responsible to give you the pale blue precipitate, it's going to be the copper CuOH2 H2O4. Okay, or if you give your answer as CuOH2, it's still accepted. But I don't want you to remember this. Okay, I don't want you to remember this because it is copper hydroxide is copper hydroxide with 4 ligands of water. Okay, please remember that. Okay, so I want you to remember the moment we see the copper, okay, the one related to precipitate. Okay, the precipitate, which is the pale blue precipitate, they are going to be the copper hydroxide, CuOH2. Then do remember, include the water, which is going to be 4 moles of water. Okay, so that is going to be the one that is going to give you the pale blue precipitate, and the answer is going to be the same over here. Okay, that is going to be the one responsible. It means, do remember, when I add few drops of ammonia, when I add excess sodium hydroxide, okay, to copper 2 plus, the reactions are the same. This is what I want you to remember. Okay, the reactions are the same. Now, if let's say I'm going to add excess ammonia, what is going to happen? Things are going to be different now. Now, if you add excess ammonia, okay, in your textbook, you will see this. This is going to be when you get, okay, let's say when you have the hydroxide, sodium hydroxide, once you get this solid, when you add with the ammonia, you are going to get a deep blue solution, okay, deep blue solution. But this one, be careful, you are starting with this, okay, but we are starting with this. So it's the reaction is almost the same, but when you write the equation, let's say they ask you to write the equation, it means that you are replacing uh, out of this water, 6 moles of water, you have to replace 4 moles of water, replace it with ammonia, and then the water molecules, the 2 water molecules will stay. It means our end product is still the same. So we are assuming, okay, what do we assume? Just take it as these 2 equations joined together, okay, and then you cancel the pale blue precipitate, okay. But okay, if you want to put it together, I've written over here. If you want to put it together, okay, it means that copper CuH2O6, okay, when I react with ammonia, okay, I am going to get, okay, do remember this one in the next page of the textbook, yeah, they mentioned that when you add drop by drop, okay, what is going to happen? You are going to have this displacement of the ligand, replacement of the ligand, substitution of ligand, sorry. This substitution of ligand, it happens step by step. Okay, it happens step by step. So if you are using excess, okay, do take note, this is excess. Okay, so this one is not few drops of NH3. Yeah, so this one is going to be as they are reacting, you are going to get this, then you are going to get this. Okay, but in total, okay, if I just put it over here, if I highlight here, this is what we are interested with, which is the same as you combine these 2 equations. Okay, it's quite the same. So it means that if you're having it in excess, you are going to get ammonia, 4 moles of ammonia, and then 2 moles of water. Okay, so that is going to give you, okay, do remember the moment you see 2 plus, it's going to be aqueous. And what is that? Okay, this is going to be deep blue solution. Okay, deep blue solution. So it means that, okay, whenever you have pale blue precipitate, remember CuOH2 H2O4. But if it is deep blue, okay, it means the ammonia, the 4 molecules of ammonia have formed 4 dative bonds, okay, to that molecule, leaving this. Okay, then the only thing that you need to remember left with Cl. Okay, this one is quite easy. Okay, Cl minus, okay, whenever they react with this copper, the complex ion of copper, okay, they will give you yellow solution, not yellow precipitate. Yeah, the precipitate can only for copper hydroxide. Okay, do remember copper hydroxide can be also written in this form. Okay, this one I already told you earlier. So here, okay, the yellow solution, okay, is going to be represented by CuCl4 2 minus. Why CuCl4 2 minus? I think Cu2 plus, Cl minus, Cl minus, Cl minus, Cl minus. Okay, so you join this one and all this, you will get -2. Okay, that's a charge. Okay, so I want you, okay, to really look into this, okay, because I have written for you all the reactions, okay, involving this copper, okay, copper ions. Okay, even here the full equation I have written for you. Okay, you can have a look. Okay, but what is important over here is, okay, if let's say you don't remember the equations and so on, what is the one that I really want you to remember is when you add few drops of ammonia, you think as though you are adding OH minus. This is what I want you to remember. Okay, So it means the reaction of adding few drops of ammonia is going to be the same as you are adding excess sodium hydroxide. Okay, so you are going to get a pale blue precipitate, and that pale blue precipitate, you know, you should know what is that. Okay, you should know what is that. The color also and so on. Okay, this one I'll leave it to you how you want to remember. Okay, but I'll pass you these notes. Okay, once it's done. Yeah. So remind me. Okay, if I forget to pass this to you. Yeah, if you need these notes. Now, next. Okay. Of course, in our syllabus, okay, if you're asking, sir, is this the only thing that I need to remember? No, not really. Therefore, there is cobalt. Okay, it's related to cobalt. And this question was related to cobalt. And I was surprised why suddenly they're asking too many about copper and then cobalt. Then I went and checked in my book and so on. I came up with all the notes. But later, only when I read the question, I saw, oh, they do not want the equation. What they want is they are trying to relate the color, okay, the change of color, cobalt to chloride. It changes from blue to pink. Okay, we need to explain this observation, but no need equation. So it means whatever things that I wrote over there is actually extra notes for you. Okay, but you need to include you need to include the reference of electron movement between the orbitals. So this one, when they mention about including the electron movement from orbitals and so on, that is already it's already indication, okay, saying that they want to see the why there is a difference in color. So you need to talk about the d orbital splitting, okay, or the non-degenerative orbitals, okay. So the answer, okay, let me discuss the answer first, okay. Why there is a color change from blue to pink? Okay, definitely there is going to be something to do with the ligand exchange. What ligands that are involved? Chloride, okay, Cl minus, and then water. Okay, these are the two ligands that are involved. Okay, so there is a ligand exchange. Because of this ligand exchange, even before, okay, even before, presence of ligand will create the two sets of non-degenerative d orbitals. Okay, so they already created. So you don't need to tell suddenly now it starts to split. No, you just need to explain that the moment you have different ligand, the magnitude, okay, the magnitude of the the magnitude of the energy, okay, the magnitude of the energy of the non-degenerative orbital, they are going to change, okay, because different ligand. So they already splitted, but now it's going to change a little bit. Once you have that, when you pass through, when you pass light, okay, when you pass through the visible light, okay, this will change, okay, the light, the amount of wavelength or the energy that is going to be absorbed by the electron, okay, from the lower energy, okay, when they are going to absorb and they become excited to go to the d orbital, okay, that has higher energy. So so that you are going to give you a complementary color, okay, to the light that is going to give, okay, after passing through the sample. So because of that, you are going to have different color. Okay. So here, what are the points that they are looking for? They are looking for ligand exchange. They are looking for the magnitude of the d-splitting is going to be different. Okay. Then the changes of wavelength of the light that is being absorbed, and you need to mention about the electron being excited, okay, from lower energy to higher energy. And then the complementary colors now will be different because different energy is going to be absorbed. Okay, so that is going to be one you answer. Okay, but I want to discuss this because we started about the equations. Okay, let's start with the cobalt. Okay, cobalt 2 plus. Now cobalt 2 plus, they always exist, okay, in this form. Okay, they always exist. Okay, they always exist in this form. Cobalt 2 plus, they always exist in this form. And the color is going to be always going to be pink. Okay, the color is always going to be pink. When you add okay, when you add hydroxide ion, sodium hydroxide and so on, you are going to have, okay, a situation where they are going to give you this, okay, CO, OH2 and water. This is not something that looks new. You can see here, similar to the copper, okay, when you add, you are going to get something similar to copper also, okay, so nothing special, okay, but the color, okay, the color, they didn't mention it in the textbook, okay, the color didn't mention it in textbook, but they mentioned that when you warm this, okay, it means when you heat up this, you are going to get a red precipitate. Okay, they said if you warm this, then you are going to get a red precipitate. Now, what will happen? Okay, what will happen if you add ammonia? Okay, what will happen when you add ammonia? This is excess ammonia. So even this one, if you are adding ammonia drop by drop, little ammonia, you are going to get this condition also. Please remember this, okay, like what I said. Okay, but now if you are adding excess ammonia, you are going to get this, okay, you are going to get this. And if you are adding, okay, if you are adding excess chloride or HCl, okay, you are going to get this, which is going to be a blue solution. Do remember, they are all pink in the beginning, okay, they are all pink in the beginning, okay, they are all pink in the beginning, but now they are going to become blue. This one, please check, okay, if I'm not mistaken, it's straw in color, I think. Okay, something like a yellowish brown kind of color. Okay, but again, here, okay, it's going to change into blue. But coming back to the question, they say that when I add cobalt to chloride, it means cobalt to chloride, they are talking about this. Okay, they're talking about this, which is going to be blue in color. When I add water, I am going to get a pink color solution. So it means that the water is exchanging with the ligand with the Cl. So you are going to get this, which is coming back from here to here, okay, which is going to be the pink color. So these are the things, okay, basically that I want you to remember, okay, memorize better, okay. But again, this one, I leave it to you as a capacity of a student. If you have that capacity to memorize this, then go ahead. Okay. If you want to skip that, I cannot blame you. But okay, I want you to focus. If let's say you want to study, you just want the basic stuff. What are the things, important things that you need to know? I have told you what are the important things that you need to know. Okay, that's why I'm spending more time over here. Okay, so if you want to know, you want to make sure that you don't lose these 4 marks. Okay, you don't want you can't afford to lose that 4 marks, for example. Then you need to focus on this. Okay, but nobody knows, okay, how it's going to be asked and so on. Okay, we won't know. If the question doesn't specify reference to electron movement, can we use LCP? Okay, if let's say they don't specify, can we use LCP? I think can, okay, because it's supposed to be like this. So when you add water, so from blue to pink, so this one, blue to pink, more water, so you dissolve, can, but I think you still need to talk about ligand exchange also, Gabriela Nico. Okay, so you cannot ignore the ligand exchange. Okay, but normally, okay, explain that it dissolves. Okay, explain it dissolves, yes, okay, but do remember the equation is important. Here no equation is needed, so you need to, if you are using the LCP, yeah, you need to write down the equation. But when you write down the equation, you still mention it's going to be ligand exchange. That cannot be said just dissolve, it's not enough. Okay, so you need to mention it's going to be a ligand exchange as well. But yes, okay, to answer that, okay, if you don't need to have any electron movement, it means you just want to explain just like that. Yeah, ligand exchange is going to be the main idea then. Okay, that will be the main idea. But equations are important if you are using the ligand exchange. So it's quite tough, okay, to remember. Okay, I do understand fully. Okay, but this one I leave it to you. Yeah, So nobody said it's going to be easy. Yeah. Especially the one that requires things to memorize. Okay, there's a lot of things. Okay, but my work is to tell that there is a way to memorize it systematically, which I'm actually helping you over here. Okay, so the one that I want you to remember is going to be the precipitate. Okay, the precipitate, which is going to be the one I highlighted here. Okay, pale blue precipitate, pale blue precipitate. So all these are coming from where? Okay, it's coming from, okay, when you replace, okay, the 2 moles of water, you replace with OH. Okay, so that is going to give you the pale blue precipitate. Okay, please remember this. Okay, now, so next, okay, when chlorine gas, okay, is going to be bubbled in FeSO4, okay, the color of the solution changes from pale green to yellow. Okay, it means that pale green, I know that it's going to be something related to my Cl2. Okay, something related to my Cl2. Now it's going to become yellow. Okay, so if I have something related to Cl2, it become yellow. So one thing that I can think of, maybe the reaction will continue. It is reacting with FeSO4. Okay, it is reacting with FeSO4. If it remains green, then no reaction. But this one, there is a reaction. So Cl2 must be, if you have Cl2, definitely they will change into Cl minus. So I can see that, okay, if Cl2 changing into Cl minus is going to be receiving electron. So if this is receiving electron, okay, this is going to be reduction is gain of electrons. So this is reduction. So if this is reduction, okay, it means that this is a very good oxidizing agent. What is the definition of oxidizing agent? Something that can oxidize others, but they will themselves will undergo reduction. So it means that the Cl2 will be able, okay, will be able to oxidize. So how to oxidize? You see Fe2 plus. Fe2 plus oxidize to become Fe3 plus. That will be the one that is happening. So all this will help me to determine which equation should I use when I refer to the data booklet. So I know that, okay, this is the equation that I need to refer. But if you're not sure, yeah, you can actually bring in and write down the 2 first, okay, bring in and write down 2. But you need to select which one, okay, because there is Fe2 plus to become Fe, okay, and there's also Fe3 plus to become Fe2 plus. So which one should we choose? So I chose, okay, this one because I know that, okay, if Cl2 is changing to Cl minus, because I'm talking about there is a reaction. Okay, if there is a reaction to become Cl minus, don't tell me that they are going to join with the solid. Impossible, right? Where the Cl minus joining with the solid. So it must be something that is having the Fe2 plus. So that's going to be another reason why I selected that equation also. Okay, so I wrote 2. Okay, I'm not sure. Okay, but I determine. Okay, I determine which one. So I determine, okay, once I have, okay, this will happen. Okay, then the use the data, okay, include an equation. Okay, include an equation, it means only one equation. So I put it like this. Okay, 1.36, this will move forward, this will move backward. So I just rearrange this. Okay, and then I can join them together, okay, by writing Cl2 plus 2 Fe2 plus. Why? I want to eliminate the 2 electrons. Okay, so it will give you this and it will give you this. Okay, so done. Okay, this one is done. You can write the same thing over here. Okay, because if you are wondering what happened to the SO4, okay, SO4 is going to be the what we call as spectator ion. Okay, SO4 is a spectator ion. So even if I write down like this, okay, SO4, then I have the 2 SO4 here. Later, what I will do, okay, I will remove the spectator ion. Okay, so I will eventually get Cl2 plus 2 Fe2 plus to give me 2 Fe3 plus 2 Cl minus. I think eventually I will also write it in this way. Okay, so how to know it is Fe2 plus, Fe3 plus, or Fe2 plus for the equation? So Shane, this one is quite simple. Okay, you see, Cl2 is reacting to Fe2 SO4. Sulfate is 2 minus. Okay, so I know Cl2 is reacting, Cl2 is reacting with Fe2 plus. So I know that there is a color change. It means there is a reaction. So if there is a reaction, I know maybe it will change into Fe3 plus, or it will change into Fe alone. Okay, I know that. Okay, but okay, I also need to know that Cl2 must also react. Okay, so Cl2 must react, okay, to give you something. So if it is reacting, the only thing that it will give is going to be Cl minus. So Cl minus must be bonded with something. Of course, Cl minus will not be bonded with the solid. Okay, so that is how I reach to the conclusion. It's supposed to be Fe3 plus and the Cl ion. So you get FeCl3. Okay, so in a simple terms, okay, so basically I'm thinking about, okay, Cl2 plus this is going to give me this. This is what is my thinking. Okay, I'm looking into this situation. Okay, so I already decided FeCl3 is going to be formed. Okay, based on whatever data that I have, I know this is going to be the one that is going to be formed. Okay, next. Ken Shane, does it answer your question? Okay, she said, okay, sir. Okay, fine. So if a solution, okay, of chloride ion is added, okay, equilibrium is going to be established. Okay, so write an expression of stability constant. So stability constant, very important thing is to ignore this water. Water is constant. Yeah. So ignore the water. Okay, so when you write down, okay, you write down FeCl4, okay, minus, okay, divided by FeH2O 6 3 plus to the power of 1 times Cl minus to the power of 4. Okay, that's going to be my stability constant. For the above equilibrium, the numerical value is given. So just replace with that value that we have, 0.08. Okay, replace. FeCl4, okay, they say 0.1. Okay, put. And then they are asking you to calculate this concentration. So I just put it as X. Okay, X. And then this one is going to be concentration of Cl minus is going to be 2. So just put 2 to the power of 4. 2 to the power of 4 is 16. Okay, so I just calculate what is X. Okay, when I calculate the X, I'm going to get this. So what I want is I'm just simply looking for 0.0781, 3 significant figures. Okay, more for them here. Or you can say 7.81 times 10 negative 2 mole diameter. Very easy, yeah? That's why it's 1 mark and 1 mark. Okay, they didn't actually really want to focus on this. Okay, so if you are wrong with the water, I think most likely you will get wrong here. But okay, you if you take the water in, you will be wondering what will happen here. What should be the value that I should be using for water? Okay, so I think the moment you have that situation, then double check again. Okay, this is also can be another way to double check. Okay, but don't simply leave it empty. That is going to be something that is going to be wrong. Okay, sometimes, okay, is you will get 0 for this, but you can still get 1 for this even though it's wrong. Okay, the second part. Okay, as long you follow, okay, you included water, okay, fine. But you need to tell me why the water, okay, that you have included, you took that value. Okay, but I don't think so there is any value related to the water. Even you try to include the water here, okay, even though I give you wrong here, okay, but if you try to include water here, you need to explain from where you get this water's concentration. If you cannot explain, then you won't get the marks. Okay, but anyway, just try. Okay, just try. Okay, so you might get the marks if you just keep on trying. But don't simply whack and then don't simply give answers just like that for the sake of showing that I don't know whether it's correct or not, but if I write a lot, maybe people will think that I'm putting in a lot of work. Yes, people will appreciate your work, okay, but that doesn't mean that they will give you mark. Okay, so please remember that. Okay, so try to make it as systematic as possible. Do not need to include things, okay, that are not going to be tested, that are not being they are not, don't include things that you shouldn't be including over there. Like for example, here I'm including here because I want you guys to learn. Okay, but if you go and include this, it's not going to do any good for you. Okay, because they didn't ask about this. Okay, next. A polymer P can be made of the monomers, okay, of this benzene 1,4-diol chloride and benzene 1,3-diamine. Okay, draw a section of polymer chain of P. Okay, your structure should include 2 repeat units. I think this one is quite I think took time to draw. Okay, but the important thing is you need to be certain what is happening over here. So you need to be certain Cl and one of the H, okay, will join together, and one of the H will join together with the Cl, and then you have Cl. So it means that if I can join this and then show 4 repeating units, okay, I can 2 repeating units, sorry, 2 repeating units. I can tell, okay, this is the polymer and I get the mark. So you can see this is 1 repeating unit, another repeating unit. So how to do, you see the Cl, okay, already reacted, okay, and then you have this Cl gone, H gone, so A plus HCl. Okay, so here the C double bond O, it is going to join with the nitrogen containing the hydrogen. So you will get something like that. Okay, you just join them together and you will get this polymer. Okay, this polymer, they didn't tell, okay, how much moles of water that you HCl that you are going to have over there and so on. They don't want you to learn about that. Okay, but okay, that's going to be the structure. Now place one tick in the table. Okay, this one read properly. Even I was doing it very fast. Okay, I also thought that they are asking for all, so I was ending up answering for all. Okay, it means I was answering polyalkene. Is it addition or condensation? So I say, okay, polyalkene is addition. Polyamide, condensation. Polyester, condensation. I end up ticking 3. Okay, but I didn't read the question properly. You need to read the question properly. They are asking that whether this reaction, one tick in this reaction to describe polymer P. So when I look at polymer P, so it's you are going to get this molecule. Okay, you are going to get this. Okay, which is going to be what we call as peptide linkage. Okay, or amide linkage. So in this case, this is going to be amide structure. If it is amide structure, we call it as polyamide. Okay, so here this should be polyamide, and the type of polymerization is going to be condensation. Addition is going to be whenever we have carbon-carbon double bond, then we have addition. So this one is a condensation reaction. Next question is this state whether the polymer P is biodegradable, and then they're asking a reason for the answer. So biodegradable means whether this polymer can be broken or not. Okay, if I look over there, the monomer, this polymer can be definitely broken. So how you break this bond? Okay, so you can do hydrolysis. Okay, hydrolysis, you can do it either with acid or you can use with the concentrated sodium hydroxide. So that bond can be broken. If it can be broken, okay, so there are 2 ways where the bonds can be broken. One is going to be through hydrolysis. Another type is going to be the photochemical reaction. It means when you have a certain amount of sunlight, okay, or UV light, okay, the bonds is going to be broken. So please read on this. Okay, but for this question, it's going to be condensation, which is related to polyamide. Now, state, okay, yeah, can be hydrolyzed. Okay, state a suitable region to produce benzene 1,4-diol, okay, chloride. It means diol chloride. It means something to do with this. From something that has benzene 1,4-dicarboxylic acid. it means something that has this. And they say dicarboxylic acid, maybe they have something like this. So I want to produce this from there. How do you produce? Okay, from carboxylic acid to become acyl chloride. Okay, you can change carboxylic acid to acyl chloride. You can change halogenoalkane to become acyl chloride. Okay, by using three methods, and I have written down all the three methods for you. You can choose. Okay, do remember it's also applicable for alcohol. It is also applicable for halogenoalkane, and now it is also going to be applicable to our question over here, which is going to be applicable to how do you form benzene 1,4-diol chloride, okay, from benzene, okay, applicable. If you are using PCl5, okay, you can reach that, okay. If you are using PCl3, if you are using SOCl2, okay, you can have, okay, the acyl chloride. But we do have side products, okay. The side products is going to be, if you are using PCl5, the side products is going to be POCl3. It's going to be one of the side products, and ACl. If you are using PCl3, the side product will be H3PO3. If you are using SOCl2, the side products will be SO2 and water. So which one you choose? Choose wisely. Okay, in this case, you can choose any three. Okay, and then they say state suitable agent. Okay, suitable agent is there. If they ask you the condition, okay, please remember this. PCl5 don't have special condition. SOCl2 don't have a special condition. But do remember SOCl2, they are used to identify alcohol group. Okay, they are used to identify alcohol group. But in this case, okay, please remember one condition. PCl3, if you want to form the H3PO3, okay, PCl3 will require heat. You cannot do this, okay, without the presence of heat. Okay, so it requires heat, and the PCl5 and SOCl2, okay, you do not need heat. Okay, the number 5. Benzene 1,3-diamine can be formed, okay, from using benzene using the reaction sequence shown. Okay, this one is quite easy. Yeah? So this one is going to be you are adding the NO2 into the benzene ring. So if you are adding NO2 into the benzene ring, okay, this is nitration. So what are the reagents that we use? Okay, we use concentrated H2SO4 and then concentrated HNO3. That's going to be the reagent. And then if they ask you conditions, okay, if they don't ask, no need to give. This one based on our previous practice in the passé paper, 50 to 55 degrees Celsius. But in our textbook, we learn as 55. Okay. Now, step 3. Here you see nitrobenzene, okay, dinitrobenzene. And then I'm going to get this. How do I get phenylamine from nitrobenzene? Okay, this reaction, okay, must be you are using concentrated nitric acid, okay, and you are using concentrated sulfuric acid. Sorry. Concentrated nitric acid and sulfuric acid is going to be for nitration. So this one you need to reduce. Okay, so you need to reduce. So therefore, okay, you are using SN, the tin, okay, and the HCl, concentrated HCl, and you heat them. Okay, tin and concentrated HCl heated, but they didn't mention about conditions, so no need to mention the condition, is still okay. Okay, tin and concentrated HCl. Proteins are natural polymers. Okay, a protein is said to have primary, secondary, and tertiary. You see here, one entire chapter, 3 marks only. Okay, not only 3 marks, I think they ask this and this. So total, I think you have 6 marks from one chapter, okay, that we have learned. So here, okay, they're asking you, okay, what is meant by primary structure? Okay, primary structure is going to be any structure that has this sequence of order of amino acids. Okay, so sequence of order of amino acids, okay, is going to be there. Okay, and then what is secondary structure? Secondary structure is going to be sequence of order of amino acids that can be existing in alpha helix and beta pleated. Okay, so alpha helix and beta pleated, they have mentioned this in the marking key, so you can also check again. So that is secondary structure. And then tertiary structure is going to be a little bit more advanced. What is the meaning of tertiary structure? It's going to be involving folding of the chain. Okay, you can have more branches, more folding of the chain, and it will give you some sort of a 3D shape. Okay, it will give you a 3D shape. And in order to maintain that 3D shape, you need to make sure, okay, that um, it means in maintain the 3D shape, it means the stabilization. Okay, the bonds are stabilized. So how do we make sure the bonds are stabilized? Because of the presence of C double bond O and NH. So these bonds, okay, not together, okay, it's an interaction between them. Okay, this interaction between them will keep the stabilization of the secondary structure. Okay, there is wait, let me think. Stabilization of structure. Okay, I wanted to say something, but I forgot. Yeah, there is another one, okay, which is going to be the quaternary structure. Okay, do remember the quaternary structure. What is going to be the one that is going to stabilize? Okay, so do remember, if it is going to be primary, it's going to be covalent. Okay, the covalent forces of attraction. If it is going to be secondary, then we are talking also, okay, for example, maybe we are going to talk about, okay, this hydrogen bonding, okay, and so on. That is going to be for secondary. But for tertiary and also for the quaternary, the the bonds that are responsible, there will be more bonds. Okay, there will be dipole dipole, there will be ion. Okay, ionic bond. Okay, if you remember, the ionic bond can exist between ions and ions. There will be also covalent bonds, I already mentioned. Okay, so there's so many bonds. Okay, so many bonds. I think the disulfide bridges, if you can remember. Okay, there's disulfide bridges. If you have sulfur and sulfur, okay, all these bonds will be responsible, okay, to the stabilization of the structure. Okay, I will move on. Yeah. Now, butane dioic acid. Okay, do we have to mention the bonds for the tertiary in the definition? For the definition, do we need to mention the bonds? No need, because they say define only. So define, it's a folding of chain to make 3D shape. So how they are being folded, how they are going to form the bond is not important. Even here, okay, alpha helix and beta pleated also, you do not need to mention why it is going to be in helical form, why it's going to be in pleated form. No need. Okay, no need to do that. Here, name the forces I already mentioned to you. It's a hydrogen bonding. It's a bonding between CO from one molecule to another NH to another molecule. So we are talking about generally this H with O. Okay, it's the bonding between H and O. So they are going to give you the hydrogen bonding. Okay, next, okay, number 8. Okay, it's already 12:30. Just give me a moment, yeah, so I can finish. Okay, butane dioic acid can be used, okay, to make a 3-step synthesis using ethane as the starting material. So you use ethane. So when you get this, okay, this one there is only a single bond saturated, and then you are going to get this. This one definitely free radical substitution. Okay, free radical substitution. And then suddenly, out of sudden, there is going to be increase in 2 number of carbons. Why suddenly there is an increase in 2 carbons? The only way that you can achieve this is by adding the carbon through this this equation, where you add the KCN in ethanol. Okay, that's the only way that you can do this. Okay, KCN with ethanol. So describe the regions and condition needed for step number 1. Okay, step number 1, the region that you need to use, okay, is going to be, you are going to use Br2 aqueous, okay, Br2 aqueous, and condition in presence of UV light, okay, UV light or sunlight, okay, UV light or sunlight. Name the other product also formed in step 1, which is an isomer of A. So they are telling isomer of A, so Br, so just use the structural isomer. Okay, the Br, just put the Br over here. That is also possible. So CCBr, Br. Okay, what do we call this? So this is going to be 1,1 dibromo ethane. Okay, 1,1 dibromo ethane. Give the structural formula of B. Okay, so this molecule. Okay, so after you add the KCN, the step 2, okay, what is going to be the structure? So the Br, okay, is going to be substituted. This is going to be nucleophilic substitution reaction. So it's going to be substituted with the Cn. So if I just draw the displayed formula first, you are going to get this Cn. So if I want to give the structural formula, so I will write down Cn CH2 Cn. Okay, that will be how you write. Okay, or I think you can also write down, okay, CH2 Cn, CH2 Cn is still the same. So this one is not bracket, yes, Cn. Now state the region and condition needed for step number 2. Okay, this one is the one, the KCN. You can use KCN. You can use NaCN. Okay, do not go and use this one, yeah. Don't go and use ACN. Okay, don't go and use ACN. This one maybe I can ask someone. Anita, why we cannot use ACN? When do we use ACN?
NaCN because
Okay. In this question, we can use KCN and NaCN, but cannot use HCN. Why? Or where do we use ACN? Because now we are using this KCN and NaCN with the halogenal alkane. Okay, halogenal alkane. So this halogenal alkane, okay, I'm going to just put the KCN, okay, or NaCN, okay, but the KCN and NaCN, okay, KCN and NaCN must be heated under reflux, okay, but must be with the presence of ethanol. Okay, why I'm not asking you to write HCN, because HCN is used for the reaction with carbonyl compounds. You go and check your textbook. Okay, so carbonyl compounds, then only you use NaCN with HCN so that you get the electrophile of Cn. Okay, this combo is only used with the nucleophilic addition reaction. Okay, this combo is only used for nucleophilic addition. So this one is KCN or NaCN. Choose one. Okay, why? Because we want all the CN. Okay, we want all the CN that we have, and then you do the reaction. Now, okay, let's go fast here. We have only 4 minutes. Okay, I want to finish by 12:40. Now, butane dioic acid cannot be oxidized by warm aqueous solution of any commonly used oxidizing agents, but ethane dioic acid can. Yeah. Now, do remember, okay, I want to teach you about this ethane dioic acid. Ethane dioic acid can be only oxidized by very strong oxidizing agent. Okay. So the only strong oxidizing agent, just acidified potassium manganate, okay, or acidified potassium dichromate. Okay, you choose one. Okay, but I want you to also learn, apart from ethane dioic acid, you can also oxidize methanoic acid. Okay, but methanoic acid is very reactive, so they can be oxidized even by any oxidizing agents. They can be oxidized by mild oxidizing agent like phthalate, toluene, also KMnO4, K2Cr2O7. So that one, any oxidizing agent, okay, will be okay. But this one, no, yeah. State the products of the reaction. Okay, the product of this reaction, if you are using it, ethane dioic, you are going to get carbon dioxide and water. Okay, you are going to get these two. Okay, I'll move on here. Compare the relative acidity. Okay, very fast here. I'll just put it. Hexanoic acid is more acidic, okay, compared to phenol, compared to hexane 1-ol. How to relate this? Why it's more acidic? Okay, you just look at this structure. Because of the carbon double bond O, the oxygen is more electronegative. They will pull the electron. So the bond between the OH is going to be weakened. Okay, the bond is going to be weakened. Okay, the same, okay, applies to phenol. Okay, but it's not weakened that much. Okay, because the electrons, they will enter will become delocalized into the benzene ring. Okay, the electrons will become delocalized into the benzene ring. So what happens? This bond is also going to be weaker, but not as weak as this. Okay, but this one for normal alcohol is going to be, R group is an electron donating group. So when they donate the electron, this bond between O and H is going to be more stronger. So it means the bond cannot be broken easily. So please look at the marking key and then explain accordingly. Okay, this one I'll leave it to you. Okay, but this one, okay, I'll just tell you why there is a single peak. Okay, a single peak can happen because, okay, the hydrogen environment, the next carbon beside that don't have any hydrogen, then only you'll get single peak. Okay, so you see, most likely is this carbon, this hydrogen, because this carbon don't have hydrogen over there, so that will give rise to single peak. Or this hydrogen also here, single peak. Why there is 4 peak? Must be adjacent to it, must have 3 hydrogen. So must be this hydrogen. Why? The carbon adjacent to this must have 3 hydrogen. So you can see, you can see it's related to, uh, okay, if the carbon, okay, related, you must have 4, sorry, must have 4. Okay, so you have this. This one, okay, Y is 2, okay, because the carbon next to it is only 1. So N plus 1, you have 2. So you just identify accordingly. Okay, it's done. Okay, next is going to be name the splitting pattern 3.3. Okay, this is going to be 4. So it's called quartet. Okay, why? Carbon next, or we don't use the next, we just say adjacent carbon. Okay, it's bonded to 3 hydrogen. Quite simple as that. Okay, and then here state the number of peak. Okay, why different number of peaks? So I wrote the, okay, I wrote the structure. Okay, it means the display formula, and then I tried to find out how many different hydrogen environment. Okay, so I know this hydrogen environment is the same as this hydrogen environment, and I know that this hydrogen environment is the same as the remaining hydrogen environment. So there are 2 environments, so 2 peak. Okay, when I have this one, okay, this hydrogen environment is the same as this hydrogen environment. Okay, and then I will also see that, okay, this hydrogen environment, okay, is different. Okay, it's different, and this hydrogen environment is different. So how many total hydrogen environment that I have? Okay, total is going to be 3 environment, which is going to lead to 3 peaks. So here when they say butane dioic acid, so 2 peak, and this is going to be 3 peak. Okay, so that's it, guys. Okay, for today. Okay, we will continue with the question number 9 next week. Okay.